All right, so something that I want to make sure that there's a video for is inverses. How do you go from a function and write its inverse? Well, there's these four steps here. The first step is to change f of x to y. So they gave us f of x is the square root of x plus 2 all over 3. So I'm going to write that as y equals the square root of x plus 2 all over 3. Then it says to interchange x and y. So literally replace y with x and x with y. Now, why do we do that? Well, inverses are taking a function and reflecting it along the line y equals x. So if we're reflecting along the line y equals x, then we replace or interchange those two. Now we solve this for y. So how do we get rid of divided by 3? Well, we multiply both sides by 3. So 3x equals the square root of y plus 2. How do we get rid of square roots? Well, we square both sides. So you end up getting 9x squared equals y plus 2. And then we subtract 2 on both sides. But how do we really denote that this new equation is an inverse? Well, we do the last step. We replace the new y with f inverse of x. So please make sure that you are using the proper notation. So that's how we write the inverse function of this square root function. Now, how do we test to see if an inverse and a function are inverses of each other? Well, we use compositions. We plug in the inverse into the function and see if it equals x. And then we could do the same thing vice versa. So let's see what happens if we plug in 9x squared minus 2 in for this function. So let's see, what was the function? The square root of, we're plugging in 9x squared minus 2 in for x. And that's all divided by 3. Well, those parentheses are just there just to kind of show that I plugged in that for x. So I'm just going to kind of get rid of it since I can. And then let's simplify this. The negative 2 plus 2 is 0, so we get the square root of 9x squared over 3. And then we square root 9x squared, which is just 3x. Now some of y'all might be, well, isn't it plus or minus? No, we didn't solve by square root. We did not square root both sides and get, to solve something. So we're just asking, what is the square root of 9x squared? And it's just positive 3x, called the principal root. So if you divide those by, simplify this fraction, you're left with x. And again, vice versa is if I plug in the original function into 9x squared. So 9 parentheses, what was the original function? The square root of x plus 2 over 3. And then square it, and then minus 2. Well, what happens if I square this fraction? Well, you square the square root, so you're left with x plus 2. Then we also square the 3 and get 9, and just add that minus 2. So 9 times this fraction, the 9's cancel off, so we're left with x plus 2 minus 2. And then simplify it even further and get x. So these are inverses of each other, because if I plugged in one into the other, I get x. This is something that we're going to ask you to do on quizzes and tests, so just make sure that you're showing all your work and making sure that you get x. You know the answer, you just kind of need to fill in the middle part. If you have any questions, let us know.
So the next thing we're going to do is some more of these, but we're going to add a notation. This open circle here, this is just another way of writing compositions where we're taking one function and plugging it into another. So sometimes you'll hear me say fog or goff. The order does matter. If it's f o g of x, then that means you're taking g of x and plugging it into f. So we have two new f of x's and g of x's here. F of x is 2x and g of x is negative x squared plus 1. So if I'm going to do fog of x, that means I'm going to take g of x and plug it into the function f. Well, g of x is this negative x squared plus 1, and I'm going to plug it into that x, into that function. So we're going to have 2, and instead of x, it's negative x squared plus 1. And make sure you fully simplify the problem. You distribute the 2, and you get your final answer. Does it matter on the order? Is fog the same thing as goth? No. If we're taking f of x and plugging it into g, it looks different. That means I'm going to take 2x and plug it in for every x that I see into g. So we end up getting negative 2x in parentheses squared plus 1. So to fully simplify it, we square the 2x, get 4x squared, and then plus 1, and that is my final answer. Don't know why that negative was so far away. So if it's in terms of x, again, we'll get an expression. If we're plugging in numbers, we should get out a number. So another way of writing this is just taking g at 3 and plugging it into f. Well, what is g at 3? We didn't already do that work earlier. So g at 3 is going to be negative 3 squared plus 1, which ends up being negative 8. So I'm plugging in negative 8 into f. Well, f is just 2x, so 2 times negative 8 is negative 16. Can we do the same function inside of the its own function? Yeah, you can do whatever you can, if we have it mathematically sound. So if I'm going to plug in f of x into f of x, I'm plugging in 2x for every x that I see. So you're doing 2x times 2. So you end up getting 4x. You can do the same thing with g if you needed to. All right, what about this next question here? So we're given two new functions. We have the square root of 4 minus x and x squared. So if I'm going to do fog of x, so that's f of g of x, I'm plugging in x squared for every x that I see in that function, which we could factor it, but it doesn't do anything, so that's our final answer. What if I'm given these two functions here? Well, I'm going to plug in g of x for every x that I see in the function. So I'm going to plug in 1 over x for every x that I see in f. Now, this is not fully simplified. You do not want to have fractions within fractions. So how do I get rid of this? Well, I'm going to multiply by 1. Well, my 1's not going to look like a normal 1. What I'm going to do is I'm going to multiply the bottom by x. And if I multiply the bottom by x, I need to multiply the top by x. What is x divided by x? 1. So I'm multiplying by 1, which is fine. It's okay to multiply 1. It makes the problem look different, but it's algebraically sound. So if I multiply every term in this by x, you end up getting 1 minus 2x over 1, which we don't need to put over 1, so I'm just going to leave it as 1 minus 2x. Okay. So again, I'm multiplying by 1, which is okay to do. All right, what about these last two questions on the page? They told us what a composition of two functions were, so this is our final answer. They want us to take it apart. And there's probably a bunch of different ways of writing this. The simpler two functions that we can talk about here is that if we're plugging in g into f, well, I can say g is the inside of this radical. I can say it's 25 minus x squared. So my original function would just be the square root of x. You could say that the original function is the square root of 25 minus x, and the second one is x squared. There's a couple of different ways that you can write it. For 8 here, I'm going to do the same thing. I'm going to take g of x and make that the inside of that, which means that my original function that I plugged in g into is just x to the 10th. You could figure out other different ways of doing it. You can say like x plus 2 maybe is squared, and then you have x to the 5th. That works as well. All right, welcome back. And what we're going to talk about in this part of our notes are limits of functions. So we have already talked about limits, and hopefully you practice those enough, but what we're talking about are limits of sequences. So sequences dealt with n are whole numbers or integers. When we're dealing with functions, we're dealing with x, which x can be any real number that we want to. So we're going to have this graph here, and we're going to use that graph to kind of determine our answers for a lot of these questions. So our question here is this graph a function? And how can you tell? Well, any graph that you have, you can use the vertical line test to check to make sure that everything works out. So if you draw all the vertical lines, there's no repeating x's, wait a minute, there's a point here and an open circle here. Is that okay? Yes. Same thing here and same thing here. As long as they're both not closed, then this is a function. So yes, this is a function we can say by the vertical line test. What type of function is this? Well, it's a bunch of pieces of different graphs, so it's what we call a piecewise function. So we are going to kind of review graphing piecewise, so make sure that you are paying attention on all that. So like what we talked about with limits of sequences, this limit is telling us as x gets closer to -4, what is our output? What is our y value? So x is -4 is here. So if I'm saying that as my x's get closer and closer to that, what y value do I end up getting? 3. So the limit as x gets closest to -4, we end up having an output of 3. What about if x goes towards 1? Well, 1 is here. As x gets closer and closer to 1, my y value is going to be 1. As x gets closer and closer to 5, then we end up getting 5. Well, wouldn't that just be saying, like, what is f at, or b at 5, or b at 1, or b at -4? Well, sometimes that works out. But then we end up having these symbols here. So notice we have a 2 at the plus sign up there, and negative sign, and then none here. Well, if we're talking about the limit as x approaches 2 with that plus sign and as an exponent, that means we're approaching 2 from the right. Okay, so we're approaching x at 2 from the right hand side of the graph. So kind of where all the positive numbers are. So 2 is here. So if I'm approaching 2 from the right part of my graph, so you can go as far right as possible, and we get closer and closer to 2, what is my output? Well, it's 3. So look at 2 going from the right, getting closer and closer to 2, we end up getting our output is 3. Well, if we have that little exponent of negative, well, you can kind of guess, yes, this is coming from the left. So from all the negative numbers. So I'm going to approach 2 from the left part of my graph. So I can go through my graph, go all the way from the left and get closer and closer to 2. And notice that my output is at 2. So again, coming from all the way from the left, tracing it till you get to 2, we end up getting our output is also 2. Well, wait a minute. If I'm coming from the right of the graph, I get 3. If I go from the left, I get 2. So what happens if I'm just approaching 2 from both sides? Well, this is where the limit does not exist. So a lot of y'all think Mean Girls, which I do too. Yes, every time you think of does not exist, think of Mean Girls. It's the best movie. So why doesn't this limit exist? Well, because I'm approaching 2 different outputs with the same input. Okay. If I were talking about what is b at 2, well, that's going to be different. This graph is defined at 2 when my input is 2. So my limit doesn't exist because it's approaching 2 different numbers from the right and the left. But it does, have a value of that function since there is a closed circle at 2. So how do we know if there is a limit of something? Well, we're going to let f be a function and let c and l be real numbers. The limit of the function as x approaches c is L if and only if the limit as x approaches that real number c from the left equals that same limit of the function, forgot to put my f of x, as x approaches c from the left gives you that same value of L. Okay, so that's just using our notation. So putting this in words, we're just saying that the function approaches the same y value from both sides. So from the left, from the right, if it approaches the same number, then the limit exists. If it doesn't, then the limit does not exist. So let's look at some examples here. So we have 4 different graphs here. If we're approaching x is 1, so our function's defined here. If we're approaching it from the right, our y value is 1, 2, 3. From the left, hey, it's also 3. So that means since both of those are the same, then the limit as x approaches 1 is 3. Well, where is our graph defined when x is 1? At 3. So all of these are the exact same number since it's just a nice line with that one point. What if we remove that point, make that open, and move that point down here? Well, if we're approaching 1 from the right, we end up getting 3. If we're approaching 1 from the left, our y value is 3. So since both of those are the exact same number, our limit exists and it's at 3. But where is my function defined when x is 1? Well, it's actually -3 because it doesn't actually happen here. This is an open circle, so the point doesn't exist here, but the point does exist here. So this is a case where they're not all the same.
All right. So in these scenarios here, just very similar to the last one, we have a line with a hole in it, but there is no point in which uh, f of x is defined when x is 1. So we still kind of get the same answers, is if I'm approaching 1 from the positive direction from the left, I'm still going to get closer and closer to this y value of 3. If you're approaching 1 from the negative direction or from the left, you're still getting closer and closer to 3. Even though you're not going to actually be 3, it's getting so close to 3, that's why we have limits. So since both of those are the exact same number, then the limit as x approaches 1 from either direction is 3. But since f at 1 is not defined, what we're going to say is that this is undefined. We don't want to put D and E. I understand, and I used to think the same way. There is no point, so the point doesn't exist. But in this scenario, since we have a hole there, it is going to be undefined. And then the last problem on this page, if we're approaching 1 from the positive direction, we're approaching it from the right, we're reaching this point here at positive 3. So as x approaches 1 from the right, it's 3. If we're approaching 1 from the left-hand direction, that's going to be down here. That y value is -1. Now, since both of those are approaching two different y values, the limit does not exist. So we want to reserve undefined for points which are not defined. There is no solid circle when x was 1 in this graph. Here, the limit doesn't exist because these two y values are different. So it's not continuous at x is 1. However, if we ask you what is f at 1, well, it's not defined here, but it is defined here by this closed circle. So we end up having a point at 1, 3, or f at 1 is 3.
So limits of functions are going to be a little easier to deal with than with limits of sequences. Limits of sequences, we have to conceptualize like what patterns are happening and big over small and all that stuff. But with functions, it's nice. Like if you're just saying that x is getting bigger and bigger, going to positive infinity, so that's going to be here. Well, where does my function, get close to it? Which is what limits are. It's like what y value are we getting to? It might not ever reach that y value. Like in this case, will it ever get to this horizontal asymptote? No. So it's going to keep approaching -2. It'll never get to -2, which is why we have limits. It gets closer and closer and closer to -2, just never gets to it. So, but the limit does exist. What about as x approaches -infinity? Well, -infinity is all the way to the left. What is my graph doing? Well, it's getting closer and closer to this horizontal asymptote. And again, I talked about how horizontal asymptotes are helping with end behavior. What happens as x goes to infinity and how x goes to -infinity. Well, it's going to get closer and closer to that same asymptote of -2. What if we're approaching 3 from the right? So 3 is this vertical asymptote. So if I'm approaching 3 from the right, it keeps going closer and closer to this vertical asymptote, just keeps getting bigger and bigger. Well, what's bigger and bigger and bigger and bigger and bigger? Infinity. What happens if we approach 3 from the left? So from our left part of the graph, we get closer and closer to 3, and then we're just going to get closer or lower and lower and lower and lower, which is -infinity. So from the right, I get positive infinity. From the left, I get -infinity. So does the limit at 3 exist? No, because we're going to two different values, positive infinity and -infinity. So our function doesn't have a limit there at 3. What if we're approaching -2? So x is -2 here. So we need to prove our existence. From the left, getting closer and closer to -2 is going to -infinity. From the right, going to -infinity. So from the left, limits -infinity. From the right, limits -infinity. So the limit exists, and they both go to -infinity. Where is our function defined at 2? Well, when x is 2, we have a point here where our value is 0.
So the next question is asking what is f at 4? Well, f at 4 is this point here. Notice that there are no closed circles anywhere here. So calculus speak, what we want to say, since we do not have a point anywhere when x is 4, the value is undefined.
What about all these functions here that don't have graphs? If you want to, you could definitely go look at a graph for each one of these and figure out where that point goes. Or there's this thing called direct substitution. What I'm going to literally do is plug in our value of x that we're trying to figure out the limit that goes to and plug it into the function. So if I plug in 1/5 into here, well, we end up getting that our limit is 4. So if you looked at a linear graph of 5x plus 3 and looked at where x is 1/5, the output would be 4. Same thing happens here. I can use direct substitution by plugging in -2 into that function, and you end up getting +9. Same thing here. I'm going to plug in -2 in for that x. Make sure that you apply the exponent first before doing any adding or subtracting. And that -2 cubed is -8, so you end up getting +14. Wait a minute, what about this one here? Well, 4 over x minus 9, that's a rational function. This has a horizontal asymptote at where? Well, the degree on the top is smaller than that on the bottom, so it's automatically 0. So if I'm thinking about a horizontal asymptote and thinking about this graph, as x gets smaller and smaller and smaller, it's going to get closer and closer to 0. What about positive infinity? What happens to my graph as my x's go bigger and bigger and bigger? Well, it's also going to approach 0 because we have a horizontal asymptote at 0. Horizontal asymptotes help with end behavior. What is happening when my x's go to -infinity? What happens when they go to positive infinity? So these are what piecewise functions look like when you're looking at the equation. So we have to be very careful with this type of situation. Well, if we were to graph this all out, we would end up, getting some numbers. Well, notice that both of these don't include 2. So since both of those don't include 2, then our function is not defined at 2. But does the limit actually exist? Well, if I'm talking about a limit of 2, I need to make sure it's from the left and from the right it works. So if I'm approaching 2 from the right, I'm talking about numbers that are bigger than 2. Well, which one of these two equations are talking about x's that are bigger than 2? Well, this first one. So let's see what happens if we end up plugging in 2 into that first equation. So plug in 2 for every x that you see, and you end up getting 0. Well, if you keep plugging in numbers like 3 or anything like that, you're going to notice that it's just going to get closer and closer to 0. So from the right, our limit is 0. What happens if I plug in 2 into the other one? Because if I'm going from the left, I'm talking about all the numbers that are less than 0. So let's see where that ends up stopping if I plug in 2 in for x. Oh, that's 0. So as x gets closer and closer to 2 from the right, that means you plug in numbers that are less than 2 and get closer and closer to 2, you end up getting 0. Well, if these are both 0, then the limit as x approaches 2 is also 0. But how is it that our function is not defined there? Well, this graph could do something weird, but at 2, 0, you end up having a hole. It's an open circle. So something can go crazy and you get some kind of graph to the right of it from the left of it, but it's approaching the same y value. It's just not defined there since it's an open circle at 2. What about this next piecewise function? So if x doesn't equal 2, then it's this equation. If x equals 2, it's this equation. So that's just telling me that if I plug in 2 into my function, I end up getting 8. Well, how do I figure out? So that's where my function is. Is that what the limit is? Well, if I were to kind of graph this out, well, if I factor out the top, you end up getting x minus 2 and x minus 3 all over x minus 2. Wait a minute, there's an x minus 2 on the top and the bottom, so I'm going to simplify that out and get x minus 3. Well, if you plug in 2 into this function, you end up getting negative 1. So you end up kind of getting a line where you have x minus 3, you have 2, negative 1, you're going to have a point there. Wait a minute. So you end up having a graph that ends up looking like this. So when x equals 2, we end up having a hole at 2, comma, negative 1. Well, if we think about our limit from the left approaches negative 1. From the right, it approaches negative 1. So that's where my limit exists. Our function is defined at 8 when x is 2, which is a removable point like this. All right, so let's talk about some more functions. Limit as x approaches 3 of 5. Well, 5, that function is just a horizontal line where y always equals 5. So if x approaches 3, then it's still going to always equal 5. So there's no value of x to actually substitute in. Same thing happens here. As x approaches pi of e, well, e is a number, it's a constant. There's no x to plug into, so it's always just e. Well, if I plug in 3 into this function, you end up getting 0 over 0. So the limit doesn't exist? No. If you have a problem like that, where if you direct substitute and you end up getting 0 over 0, you're most likely going to need to factor and eliminate in order to get an expression to actually plug in 3 into. So if you plug in 3 now, you end up getting 6. So you end up kind of figuring out what the hole is and where it is. So this next one, we'll get 0 over 0, so we end up factoring it, eliminating, and being able to plug in our direct substitution and end up getting 16. What about this one here? Well, we can't factor it. So what ends up happening here? Well, now you can kind of think about our limit of sequences. We have a bigger function divided by a smaller function. Well, bigger divided by small always goes to infinity. Well, what if we have x is 1 of that same function? Well, let's see what happens if we direct substitute. If I plug in 1 into the top and the bottom, well, 1 cubed is 1, minus 2 is negative 1, and then 1 squared is 1, plus 1 is a half. So, or 2, which ends up giving us negative a half. What about this equation here? If I direct substitute 0 in, you get 0 over 0. So how do we fully simplify this? Well, in order to get rid of the absolute value, what we do, if we say that the absolute value of x equals 5, then x equals plus or minus 5. So we can kind of do the same thing. We can do where the absolute value of x, I can take it apart as positive negative x, which then I can simplify and get left with plus or minus x. Well, this graph ends up looking kind of like an absolute value graph. but we can't have any values that are less than x because both of these are always going to be positive. So what happens as you approach 0 from either side? Well, you end up getting 0. This next one, if we direct substitute, we end up getting 0 over 0, so we need to factor it. And we see that we can eliminate something, and then we're left with x minus 2, where I can direct substitute and end up getting -3. Number 16 here, same idea. If I direct substitute 2, you end up getting 0 over 0, so we need to factor it. This is a difference of 2 cubes, since 8 is 2 cubes, so we're going to do SOAP. So same sign, opposite sign, and then always positive, all over x minus 2, which we can now eliminate. And if I plug in 2 into this, you end up getting 12. Again, this is something that you need to make sure you're reviewing from Algebra 2 on how to factor sum and difference of 2 cubes. What about as x approaches 5 of pi? Well, if it's pi, there's no variable. Pi is a number, so there's no x to plug into, so it's always pi. Same thing for this one. If I plug in 0 into the x, there is no x, so it's always 13. If I substitute in the 5, you end up getting 2 times 5, which is 10. And in this last one here, if you end up plugging in -1 into all of those, you end up getting 3. If you plug it into the bottom, you end up getting 1. So your answer is 3.
All right. What we're going to do at the bottom of this page is talk about two very specific functions that you will see in this class. The first one is abbreviated SGN of x. This is the signum graph. We're going to kind of review this a little bit more later, where this is very similar to the graph of x over the absolute value of x, which if you're dividing any x by the absolute value of x, well, if x is positive, you end up getting 1. However, you can't plug in 0, so we get an open circle there. However, if you plug in any value that's negative, you're going to get an open circle at 0 again, 0, -1, and you're always going to get -1. Just plug in numbers. So this function, you can kind of break it up into a piecewise function. It's 1 when x is positive. It's -1 when x is negative. So if we're talking about x over the absolute value of x, that's the only part of the graph that you have. But signum is different. Signum is actually defined at 0. When x is 0, signum outputs 0. So again, the signum graph is very similar to the graph of x over absolute value of x. However, it's defined at 0. So this is a signum graph. So if you are going to transform this like you will on the assignment, this is your parent function. Shift it left, right, up, and down. All right, so then this next graph is something that we talked about Unit 1 of the fall semester. This is called the greatest integer function. This is a function in which it rounds down anything that it's inputted. If you wanted to kind of see what this graph looks like in Desmos, it doesn't have this symbol, so what you actually have to type in is floor. So if any of the transformations that we do in this class, you can do floor of x, and it's going to be the exact same thing as the absolute value of x. There is a function that rounds up, and if you wanted to use that in Desmos, it would be the ceiling, because floor down rounds down, ceiling up rounds up. So the greatest integer function is that step function that starts with a closed circle and open circle, and then just goes on forever. What I usually like to do is draw the middle and then go 2 to the right and then 2 to the left. And if you want to show that this goes on forever, you can just put ellipses here and there.